All right. Good afternoon, everyone. I think it's time to start. So first of all, our homework 0 is due on this Friday. So if you haven't started, please start right now because there are quite a few problems. And some of it might request you to open the books you have read through during the undergrad study. So it's just a practice of calculus, basic statistics, and also kind of self-test, right? Your background. Well, if you're feeling good with that, that's good. Let us continue. If you're sick of it, yeah, then it's better to make a decision early, right? Okay, so let us continue with the review of basics as we mentioned in last lecture, right? This review is neither in-depth or comprehensive, but we just want to point out a few topics which are of importance in our future lectures, and we want to give you the guidance, give you the key ideas, and we won't ask you to memorize a lot of details because all those are provided in our references. So you don't need to memorize that. You just need to know the basic calculation rules, the idea, the intuition, and after that, I mean, as a grad student, you should be able to figure out what to do with detailed problems. Okay, so the first thing we discussed, starting from last lecture, is the matrix and vector derivative. So we first introduced the standard notations, right? So if we have a saying like non-bold letters, no matter it's capital or small, or just Greek letters, if it's non-bold, usually by default, we view them as scalars. But for small letters, if their font is bold, we usually refer them to as some vectors. And for both capital letters, no matter it's Greek letter or just alphabets, they're just they usually indicate matrices. It is kind of like a common standard across the engineering or scientific domain. So you should be aware of that. And when you read the literature, I mean, once you meet such kind of symbols, the first thing that comes into your mind should be, okay, if this guy is a vector or matrix, if it is, what is the size? What is shape? It is column vector or row vector. If it is matrix, what's the size? So you should keep this in mind. Otherwise, you're going to lose. You're going to lose yourself in those papers or formulas. And then we introduced the notions of the matrix or vector derivatives, right? So no matter you're dealing with scalar input, scalar output, or vector input, scalar output, or vector input, vector output. So everything, they can be summarized in one framework, that is the derivative framework, right? So that's what we have learned from our first year undergrad study, right? That's calculus. The basic calculus tells us that if you expand your function, your output function, at your input plus a small derivative, dx, then according to the Taylor theorem, it is your function at x plus some term times dx and plus some higher order terms, right? So higher order terms just means, okay, if your dx is small enough, of course, when we say small, when x is the input vector, dx will be vector, right? When we talk about small, you have to point out in what sense is small, right? Really, we mean, okay, it's the Euclidean norm is small, whatever. But it just means if the dx is small, then this term can be ignored. So you can use a linear function to approximate your function value at dx step away. Okay, so and the coefficient or the slope of this linear function is called a derivative. Right? It's called derivative, and we can write. I mean, this is a common notation, right? We can write dy, meaning the derivative of the output is this a times d of x, right? And we know that, I mean, from our calculus, we know that A is defined as Jacobian, right? If your output Y is m dimensional, right? M dimensional. If your input is n dimensional, then your derivative matrix A is m by n, right? So each row corresponds to the partial derivative for one particular Y element going over each partial derivative of each X element, right? And each column, of course, corresponds to a different XS element, right? So that's the definition of Jacobian and also definition of derivative, right? And this case actually covers all cases, right? If you have a scalar output, this is scalar, then A becomes a row vector, right? Because your number of rows is just one, right? If it is a Y is scalar and X is scalar, then this A becomes a scalar, right? So given this definition, actually, you have two choices to define your gradient, right? So I prefer to define the gradient by just using the Jacobian matrix, meaning that I define my partial derivative Y over partial derivative X as A. Okay? So, but there are other books or references, you might say, they take the transpose of A, right? So, but in whatever notations, with whatever notations, if you want to calculate the gradient, you still need to get the derivative, right? So the K is to get the derivative, right? We just want to clarify the notation differences so that in the future, if you look at some literature, they use different notations, you won't get confused, right? Now we'll talk about what's the benefit, what is pros, what is constraints for our different notations. If we stick to the original Jacobian, the biggest benefit will be, okay, you can just apply the chain rule very naturally from left to right, right? We use this example. Suppose your output function Y is a composite function, right? It's a function of X, X is a function of Z, and Y is m by 1, X is n by 1, and Z is q by 1. If you want to calculate partial Y over partial Z by using the Jacobian as defined as a gradient, you can just apply the chain rule left to right, right? You can just calculate partial Y over partial X, and then times partial X over partial Z. Right? Because partial Y over partial X, according to our definition, will be n by n, right? And partial X over partial Z will be n by q. You multiply them together, you get n by q Jacobian, which is our partial Y over partial Z. Right? This is very natural. However, if you choose to use transpose of Jacobian, if you define your gradient in this way, and then you have to do this chain rule from right to left, right, to match the matrix sizes. Right? So that's something I feel awkward. I don't like it at all. But that does not mean like if you use partial Y or partial X is right, Jacobian has no problem. The problem is that, okay, if your Y is simply a scalar, then your gradient will be a row vector. Remember, Jacobian, the number of rows corresponds to the number of the output elements, right? If your output is just a scalar, so you only have one row. This is actually the Jacobian is deteriorated to a row vector. So that means your definition, your gradient of the scalar with respect to a vector will be a row vector. That's something, I mean, some people feel like uncomfortable, but to me, it's fine. If you choose a transpose, well, row vector after transpose, it becomes a column vector, which might be more natural to some people. But anyway, this is just your choice of notations. It doesn't change the nature about how you calculate the gradient or how you calculate the derivative, because no matter you use A or A transpose, the the most important step is to get A, right? So we talk about how to get A, right? So this is some notes we made last lecture. Well, let me clean that. So we use this scalar case as an example to show actually it follows exactly the same procedure we did for scalar function derivative computation, right? Which we all are very familiar with, right? So it's basically just decompose your function into different components and apply the derivative rule, right? And recursively and or in a nested way until you get to some expression like dy equals a dx, then you got the derivative, right? So we use this simple example to showcase how we do that, right? So I believe everyone is familiar with that. Like if you want to take dy, you see that it's just a summation of two terms, right? So that means the derivative of summation is a summation of derivatives, right? You're going to take a derivative over 3x or 1 over x squared, right? And then you just do this divide and conquer strategy, right? You take a derivative of 3x is 3 dx, and then you take derivative 1 over x squared. You know, we have a lot of rules to do that, right? So similarly, if you got some vector functions or functional vectors, you take a derivative with respect to that input vector, you follow the same procedure. You're going to use some divide and conquer strategy to recursively apply the derivative over each components and then merge them together until you arrange some terms, something like dy equals to a times dx. Then your a is your gradient, right? So, but the major issue is that we actually maybe some of you have knowing that, but some of you might not have heard of that. What is the basic rule, right? Like, suppose you want to your function, one of term your function is dx inverse, right? So how do you compute the derivative of an inverse of a matrix? Or if your component is a log determined of your matrix, right? How do you compute that derivative? So the good thing is that we actually have summarized a lot of basic rules for that. So you don't need to worry about how to derive those, how to prove that. I mean, some very smart guys, smart pioneers, they have summarized those rules for you. So what you need to do is just follow the rules to decompose your vector functions and reach out to each individual term and apply those rules, right? And until you end up with the coefficient along with each dx, and you merge them together. Okay, that's actually the general strategy. So now I want to showcase two examples to give you a sense how to. I mean, this is kind of like dictionary learning, right? I'm trying to look up this dictionary, and then recursively apply the chain rule and to get to the derivative of each basic components, and then I just merge them together to get my final derivative, and then I can get my gradient. Right? Okay, any questions so far before we proceed to the example? Okay, so let us look at the first one. Okay. So this function y is scalar, right? So it is actually an inner product between two vectors, right? So x plus b transpose x plus b, right? So we want to take dy, right? So it's d x plus b transpose x plus b, right? So I want to decompose this, right? So in scalar world, we know, okay, if I have two scalars, dx, y, right? We know this dx times y plus x times dy, right? Everybody knows that, right? And for matrix or vector cases, they follow the same rule. So you actually can find this. Right? So you can see this rule. And sorry, this is I just copied from the reference, so they use partial, but you can view it is exchangeable with D. Right? So, so you can see that dxy, x and y are both matrices. Right? It is equal to take derivative over x times y and plus x takes derivative over y. Right? But only thing, please be aware, you cannot freely change the multiplication order. In the scalar case, well, you can freely change, right? X times y equals y times x, right? But for matrix and vector operations, you cannot move y in front of partial x because you cannot guarantee the size will match, right? So we get this first rule, right? We use this rule to decompose this dy. You can see this guy and this guy just you can view it as a matrix multiplication, right? So that means this is equal to, right? First, you're gonna apply the derivative of the first term in the product, right? Then multiply with x plus b. And second, you take the first term out and then apply the derivative over the second term. Right? Right? And then let us continue to do that, right? For this guy, right? For this guy. So the derivative of a matrix transpose is a transpose of the derivative. We can find this basic rule from here. Okay? If you do a transpose of a matrix and take derivative, it is equivalent to first do a derivative and do the transpose. Okay? So apply this, right? We can do the derivative first. So dx plus b, well, b is a constant, so you can just, you know, the derivative is simply 0, right? So dx plus b is simply dx. Then you take transpose x plus b, right? This is the first term. And the second one is easy, just dx. Okay. Any questions so far? Okay. So now, here comes a problem, right? So remember, we want to organize our result in the form such that we can write dy equals to a times dx, right? And you can extract a as your gradient, right? But right now, how can we merge the terms into this form? Right now, we have dx transpose times x plus b. Right? How do you merge those terms in terms of dx? Any idea? Yes, exactly. Exactly. Very good. Very good. Yeah. So basically, if you want to do this merge, that's why I always emphasize that you need to look at the size of each terms and what are they doing, right? So we know that the first term ends up with a scalar, right? This is essentially doing vector in the product, right? So it doesn't matter if you do A transpose B or B transpose A, right? They end up with the same result. So I can instead take the transpose of the scalar. This transpose scalar is the scalar itself. So if I take this transpose of scalar, it will be x plus b transpose dx, right? They are the same thing because they are just a number. And then I add up the second term. So what do we get? What do we get? Yeah, they both are same, right? So it's just the 2 x plus b transpose dx, right? So now let us look at the result we get so far, right? We got dy equals to this guy times dx, right? So this is consistent with the general form we want, right? So now, what is A? What is A here? Yes, right? This term, 2 x plus b transpose, right? This is your A. So this is your derivative, and this is your gradient. And now, up to you, you can choose to use this 2 x plus b transpose, which is a row vector, as your gradient, or you want to take transpose to make it a column vector as your gradient. It's up to you. But the K computation has already been done. Does it make sense? Is it relatively easy? Okay, so now let us do a little bit more complex case here, right? So this guy is dy equals to some trace operator. I is identity matrix. X transpose, X is here is vector. So X transpose is essentially an auto product. It's also a matrix, right? So, and then I'm gonna take the inverse of this matrix and then take the trace, right? So I believe everyone knows what does trace mean, right? Trace just means you just sum up all the diagonal elements in a matrix. So basically, trace is only valid for square matrices, right? So again, we want to apply the chain rule here, right? So in general, you can view. Oops, sorry. This guy as a whole, right? So let us denote as S, right? So dy equals to d, so put d here, trace S, right? So let us look at our dictionary to see how we apply the derivative over some trace function. So here, okay, let me clean them. Oops. So from our dictionary, we can find that the rule tells us if we want to take the derivative of the trace function, it is equivalent to you take the derivative inside the trace and then do the trace. Okay. So this is quite intuitive. Right? Imagine that you have a big matrix, right? And your trace simply sums up the diagonal elements. You take the derivative over the summation of diagonal elements, which is equivalent to you take the derivative over each matrix elements, and then you take the trace. Right? This is the same thing, right? So this is pretty intuitive. So, but we can follow this basic rule. We can apply the chain rule, right? So here we're gonna switch trace and the derivative over S. So that means we're gonna compute trace of d of this guy. Okay. So now it seems that we got to solve another problem. Right? We need to take the derivative of inverse of matrix. Again, let us look up the dictionary. Right? So if you look up dictionary, you can see that very smart guy, very smart pioneer people have a summarized rule. It tells us that the derivative of matrix inverse is equal to minus matrix inverse times the derivative of x times x inverse. So now you just apply this. Okay? Don't ask why, right? If you want to, if you have enough time if you have enough time, of course you can dig out why they can get to this, right? But this is some mathematicians, right? Very smart people, they summarize, right? So now we'll apply this, right? So it is equal to, you know, we need to put a minus sign here, and then take the inverse of matrix, and then apply the identity plus XX transpose, and then I plus XX transpose inverse again. Plus XX transpose inverse again. Right? This is just to apply the rule we have seen, right? So now you can see that we have some derivative operation inside the matrix product, right? So let us look at this time. What is this derivative? First, identity is constant, right? D of I is simply 0. Yes, derivative of x transpose. And derivative of x transpose is what? No, right now we cannot write 2 something like that. Let us just apply the rule. I mean, step by step. Right? Don't go quick. So we just apply the rule that here, right? So the derivative of x times y is derivative of x times y plus x derivative of y. Right? Let us just strictly follow this rule, right? And see if we can, you know, find some same term and then merge them by multiplying a constant 2. Right? So this guy is dx x transpose plus x dx transpose. Right? So this is this derivative term in the middle, right? But the reason why we can't just multiplying 2 in that is that because it is in the middle of the matrix product, we cannot directly merge them here. So I have to make some operations. Right? You have to take some transpose to have your dx on the right. On the right hand. Right? So here we need to leverage some properties of trace operations. That's very well-known properties. Maybe you haven't heard, but if you don't heard, never mind. If you do trace of the product of 3 matrices, like by default, we assume all those matrices are just consistent in size in a product. Right? So this is equivalent to, you can rotate this multiplication. Yeah, anyway. So basically, you can move C to the front. Right? So this C is B, and you can move B to the front. Trace B, C, A, right? If you move A again to the front, you end up with ABC again. So this is a very popular, very well-known property of trace operations, right? And it's not hard to prove that. It's just a little bit, you know, tedious. You need to think about why this is, but it's definitely not hard to prove. So now, remember, we always want to get a general form, dy times a dx, something like that, right? So of course we need to, we cannot give some dx and b, right? This is not, if it has such kind of form, we cannot take out the derivative, right? We must make some operations to get this form, right? And for, of course, in dx, you know, dx x transpose and x dx transpose are inside the matrix product, and then you know, in the outer level, there's trace operator is far from our standard form, right? Our final form. Of course, we need to make some operations to merge the terms, right? So, so first of all, we can apply this property. We can move the right matrix in the product to the front, right? This is just applying the trace property. So, of course, if you're a negative sign inside trace, you can take it out. It's, it doesn't change anything. So we move this I plus XX transpose inverse in the front. So actually multiply XX transpose minus inverse twice. So for convenience, I just take the power -2, right? This is just mean you multiply I plus XX transpose inverse twice. Okay. And then you got this DIX X transpose on the right, right? And from the derivative, we know that this DIX transpose is this guy, right? So you gotta have this DX X transpose plus X DX transpose. Okay, is that any question? Okay, so
why can we just simplify it to X transpose like the previous question?
because this derivative is a matrix.
X in this case is a matrix.
Yeah, no, X is a vector, but DX X transpose is matrix.
Oh,
Yeah, you cannot. If you do the matrix product, you cannot. I mean, freely just change the order. Any other question? Okay. So now let us look at one by one, right? So we can view as okay, this guy times this guy and this guy times this guy, right? So we can do it one by one. So let me put it down. -2 dx x transpose minus trace I plus x transpose -2 x dx transpose, right? This is actually assume that you know trace A plus B is trace A plus trace B. Okay. This is also intuitive, right? Okay, so now let us look at each term, each trace term, right? So for this guy, applying this rule again, we can move X transpose to the front. Okay. So you got minus trace X transpose I plus X transpose -2 dx in this trace, right? And how about this guy? Any suggestion for the for deal with this? Yes, exactly. Right. So this is another property of trace, right? If you take a trace of A times B, A is equivalent to take trace B transpose A transpose. Why? Yeah, the diagonal element won't change, right? You take a transpose, diagonal won't change. Right? The trace is always summation of diagonal elements. No matter you take transpose or not, it doesn't change the summation of diagonal. So, so we take transpose of A times B, it is B transpose A transpose, right? So here, if we take transpose, sorry, you get minus trace dx x transpose I plus x transpose minus 2. Okay. So now applying this rotation rule again, you can move dx to the end. You can move dx to the end. So end up with minus trace x transpose I plus x transpose minus 2 dx. Okay. So now let us look at these two terms. What? Oh, what's wrong with that? Does this look better? Oh, this is too small, right? Okay, sorry. So you can see these two terms actually now we see they're identical, right? The same term. After this, rotations and transpose, well, now it's the same thing, right? So we can just merge them together. So let me erase something. So now what we get is dy times, because this term is the same, right? So just times 2, right? Minus 2 trace x transpose I plus x transpose minus 2 dx. So now it's very closer to the final step. Right? Remember, in the final step, we want dy times a dx. We want to identify this a, right? So now, who can tell me what's this a? Why can we move it outside trees? Yeah, of course we need to move them, but why can't we move them out? Yes, exactly, right? That's why. I mean, in our calculation, our derivation, we always need to notice the size, right? So this guy is actually a scalar. Why? You can see that this is vector times a vector. Dx is vector, and the x transpose times this matrix is a row vector, right? So times dx is a scalar. So that means trace, we can get rid of trace, or in other words, as you just said, move them out. So you get minus 2 x transpose I plus x transpose. Well, I mean, to be more accurate, I'm now going to use this minus power of minus 2, right? Dx. So this is your A, and this is your gradient. Okay. This is a little bit harder case, but it's not. I mean, I wouldn't say it's harder, but it's a little bit more tedious case. But I want to just use this example to show how we should look up dictionary and apply them to in a chain rule and merge the terms together, and then finally arrange all the terms to get this general form, and then you get your final gradient. Any questions so far? What?
How do you find out that the x transpose multiplied by y plus x transpose is scalar?
Okay, x is vector, right? So this I plus x transpose minus 2, this is a square matrix. So x transpose times a square matrix will be a row vector. And dx is a column vector. So row vector times a column vector is just scalar. If you do the trace over a scalar, it is equivalent to do nothing, right? So you can just remove trace. Yeah, I mean, hopefully this a relatively more tedious procedure can give you a sense how, I mean, in your research, you want to take some derivative over some similarly complex functions, what you should do, right? Especially when they involve matrices and vectors. It's doing, the procedure is exactly the same as what you do in the scalar case. The only thing different is that, okay, you need to pay attention to the matrix vector sizes. You have to involve more operations like trace, like matrix inverse, but they all have rules. Does it make sense? Okay, I mean, regarding the homework problems, there are a few problems. Actually, it's kind of as tedious as this. It's just the practice. Like if you can carefully apply this procedure and look up the reference, right, those guys, and apply them recursively and arrange them, and finally you get all the results. It's not hard. It's just a little bit tedious. So
should X and Y are same dimension?
Which part?
X and Y.
Yeah, of course. By default, of course. Yeah. If you're saying X plus Y, right? When we write X plus Y, by default, we assume they're in the same size, right? Otherwise, how do you add them together? You have to assume their size or their size match to conduct the multiplication, right? Otherwise, you won't do that, right? So if we say, okay, you have X times Y, right? They must have some M by N by Q size, right? Otherwise, this multiplication won't be valid. We write it out, we assume, okay, it's already been valid. Any other question?
Always find a thing?
It's not always.
Okay.
Yeah, I can tell you, there are a few very complicated cases. It's not hard. It's not easy to arrange such kind of form, and I did that. I met such kind of situations in my study. Like if you're doing Gaussian process, to calculate the derivative of the log likelihood with respect to kernel parameters, actually it's not easy to arrange that term. Actually, it's not. But once you got this whole idea in your mind, even you cannot arrange them, you can imagine, okay, your derivative of each kernel parameters, where should they be placed in the matrices? Then you can know how to extract corresponding coefficients and merge them together. So it's not always, I mean, you can arrange this nice form, but once you get familiar with this, you can find a way to compute them. Not to mention right now, actually, I mean, because the automatic differentiation libraries are very popular. So in most cases, you won't need to derive this by yourself. This is just for your research convenience. Or in some weird cases, like you cannot apply the automatic differentiation library directly. For example, if you're dealing with some Kronecker product, something, right? If you just do Kronecker product and then apply automatic differentiation, it's much slower. You have to leverage their properties and simplify your formulation, and then apply the automatic differentiation libraries. But anyway, you need to know how to do that, because in our introduction of their models, especially in the training procedure, right? You need to know how to like EM algorithm, right? You need to know how to derive the gradient and how to set the gradient to be 0, so you know how to get to the variational update of those posteriors. If you just calculate gradient and throw them to some package, well, but you don't know there are on the line. There are some closed forms. Okay, any question regarding this? Hopefully, let's go. This will give you will give you enough guidance. Okay, so here I want to recommend 2 references, and you can click the link in our slides. It will point to the PDF. So the first one is written by Tom Minka in 2001. He was still in MIT, I guess. And this is a very good one. I love this. I love the first reference because it not only gives you the result, it also tells you the idea. So when I was in my first year of PhD program, I just spent like a weekend to go through this reference, and then I get to know everything. Right? And another popular reference is called Matrix Cookbook. It's just they summarize all kinds of basic rules, it's just a dictionary. It's just a dictionary. When you do the calculation, you find something you cannot deal with that, just to, look up the Matrix Cookbook and find the corresponding formula, and then substitute into your calculation and go on. That's it. Okay. And if you still feel a little bit difficult or uncomfortable, you want more practice and some more examples, I will post. I have posted this tutorial made by my student. He did this tutorial before, and he spent one whole lecture introducing this. And many students, I mean, previous students, felt like really great about this lecture. So if you have time, or if you feel necessary, you can just watch this video. Okay, now let us talk about convex functions. So to define convex functions, we need to first define convex regions or convex set. So the intuition of this definition is that your domain is convex if the domain is kind of like outward in every direction. So what does it mean? It means that if this is your convex region, if you pick arbitrary 2 points, you connect them, and all the points on the segment which connect 2 points must be inside this region. This is called convex region, right? So for this, you can check this, right? You can pick arbitrary 2 points, right? They are always, all the points on the segment connecting 2 points, they still stay inside this region. Right? But for this guy, so this kidney-like region, if you pick 1 point here, 1 point here, so you can see that this right part, they actually stay outside. So this is not convex set. It's not convex region. Okay. So now, given a convex domain or convex region, we can define a convex function. The convex function requires that your input domain is convex. Right? And if for arbitrary 2 inputs in your domain, right? If you can find arbitrary combination coefficient t, your function satisfies this inequality. That is, when you evaluate the combination of these 2 points, x1, x2, in terms of this t, right? This function value is smaller than or equal to the combination of the function values at these 2 inputs, according to t as well. This is kind of like a you have to use very lengthy words, sentences to describe this idea, but it's really straightforward, right? So here we just give some graph visualization, right? So this is f of x is a convex function, right? If you take any 2 inputs, right, the input region or your domain is just this x-axis. Of course, it's convex, right? So if you take arbitrary t, right, then tx1 plus 1 minus tx2 is just some point in the middle. And then we can see that the function evaluated at this combination of the inputs is here, but the combination of the function values at these 2 inputs is at here. Right? Of course, this value is less than this value. That means they satisfy this inequality. Right? If for arbitrary 2 inputs in your domain, an arbitrary combination coefficient t, they always satisfy this inequality, then the function is convex. Yeah, I believe everyone has heard of this definition, so I won't waste more time explaining the idea, right? Unless you have some other question. Okay. So here are some commonly used convex functions, exponential functions, negative logarithm of x, right? And then what is logarithm of x? Yeah, concave function, right? So concave function just means the definition is the same, except that you're gonna switch the you're gonna change the less than equal to bigger than or equal to, right? You just change the direction of the inequality. Then if the function satisfies this with changed direction of this inequality, this is called concave. Right? And log function is a concave function. Something like that is concave function. And for multivariate function, like linear function, I mean, in the optimization domain, they usually call this affine function. Okay? I don't see the difference. I don't know why they call it affine function. But this is also a convex function, and also it is a concave function. Why? Yeah, because they always satisfy the equality, right? So that means it fits both less than equal to or bigger than equal to, right? So these are both convex and concave functions. And you might see some like more definition like a strongly convex function, strongly concave function. They just means that they do not allow the existence of equal, right? They put it strictly less than or bigger than or strictly bigger than, then they call like a strongly convex or strongly concave. And this guy, half x transpose x, right? This is very common used terms in machine learning. This is a convex function. So given function, how do we check this is a convex function or not convex function, right? Of course, we can try to prove this with the definition, right? You can prove if you can prove this general inequality. If you can prove this inequality holds for general x1, x2, and t, of course you can show that. But there are two commonly used idea, right? One is to check if this function is differentiable. If you can show that for arbitrary x and y in your domain, this inequality always holds, and then f of x is convex. So what does that mean? So if you write down, if you draw a convex function, right? Suppose this is your input position y, right? So what does the right hand side mean? Yeah, I heard that. It's a tangent line. Mm-hmm. Yes. Right. This is actually the right hand side actually define a tangent line which passes through y and f of y. Okay. So this inequality actually tells us, you can pick up any point at your function body, you draw a tangent line. And then every function value is bigger than or equal to that tangent line. So basically it says for a convex function, it stays above all of its tangent lines. That's what this inequality tells us. Okay. So if you draw another, if you pick out another y, right? But here you draw another tangent line, right? You can see that all the functions, function values, will stay above this tangent line. This is basically what this inequality says. And the second And the common used checking condition is that take the Hessian, right? Calculate second order derivative, which is Hessian matrix. If you can show that the Hessian matrix is a positive semi-definite, then it is convex as well. Right? But as to why, right? This needs a little bit analysis techniques. Right? We won't cover here, right? But just to give you a sense, right? So you can use this condition immediately check this quadratic function, half x transpose x. What's the Hessian of this function? Give me a guess. No, it's a Hessian matrix, right? It won't be one.
But Fx is scalar.
X is a vector, right? So the gradient of fx is a vector, right? If you take the gradient of the vector, it will be a Jacobian matrix, right? Yeah. But just give me a guess. What's the Hessian of this? It's a Hessian matrix of this particular function. Yes, identity, right? More accurately, should be half of identity. Right? And I will leave this exercise for you guys, right, to check why. Okay. And associated with the convex function is the well-known Jensen's inequality. And later we'll know that Jensen's inequality actually is a foundation of the approximate Bayesian inference, especially the variational inference. So all the variational inference, the whole framework is derived based upon Jensen's inequality. So what does Jensen's inequality mean, right? You just talk about when you have a random variable, right? You calculate the function value with respect to random variable. What conclusion can we draw, right? So it says that if you take an expectation of x, and then you take the function f or that, this value is less than or equal to, you take the expectation of f of x. Remember, x is a random variable, so f of x is a random variable as well. So your expectation of f of x, of course, is valid because it is taking expectation of another random variable. So it says that, okay, if you take the expectation over the input and then take the convex function, it is less than or equal to, you first take the input, take the function over the input, and then take the expectation. If we consider, a concrete case, like suppose your x is it's just discrete variable, right? So it might take value like a1, p1, like you have a1, a2 to an, right? So each of them has a probability p1, p2 to pn, right? So if you can check this, so expectation of x will be, a summation of this n points, right? Weighted by the corresponding probability. Sorry. It's pj, aj, right? This is your expectation, right? But it is less than or equal to, you take each possible value that x can take, and then take expectation, which will be summation over 1 to n and pj f of aj. Okay. So this can give you a lot of results. Quite a few like well-known inequalities are coming from Jensen's inequality. And further, if you apply some transformation over x, you call gx, right? G of x is another random variable. So you can apply this again, so you got this. Right? So basically that means, okay, if you can identify some expectation and f, such kind of nested structure in your your function, your expression, you can just apply Jensen's inequality. Any questions so far? What is the, can you say it again?
Why do you consider the same probability for A1, for instance, and F of A1?
Oh, so if you have n possible values that x can take, right? Of course, I cannot guarantee that the probability of FA1 will take P1 because F of A1, because maybe this is a A1, A2 will map to the same value, right? But this equation is still valid in that if A1, A2 map to the same value, so their probability will be P1 plus P2, right? So you do this is the same thing because I'm gonna summation over all possible values. So you can consider you use merging, right? You merge them together, you end up with the same result. Any other question? Okay. So now I want to introduce another very important property or result related to convex function. It's called convex conjugate or Fractional duality. Right? It's very common used in convex optimization. If you have taken some convex optimization course before, you should have heard of that. If you haven't, if you didn't heard, you haven't heard of that, that doesn't matter. So basically, for any convex function, right, this convex conjugate tells us there exists a duality function G. Right? We can represent F in terms of G. We can represent G in terms of F. That's why it's called duality. Right? So how can we represent them by each other? Right? So F of X is the maximum of another function. That function has two inputs. One is lambda, one is x. So this is another function. You max them with respect to lambda. This is f of x. And this function is a linear term, lambda times x, minus g of lambda. And g, as we just mentioned, it is a duality, right? And alternatively, g of lambda is the maximum of lambda x, the same linear term, subtracted by f of x. But now you're maximizing over x. So literally, you can view like, okay, if I want to get a convex function, right, I can get that by maximizing a function with linear form. Right? So we can view this guy as some x and lambda. Okay? And this guy, if you fix lambda, well, it's just a linear function to x, right? Similarly, we'll want to get to the duality G, right? So actually, you can obtain it by maximizing some function h hat x lambda, right? But now we fix lambda, we maximize over x. Now I want to give you some intuition about this. Right? What does it mean? Right? So let us first look at like the meaning of g of lambda. Right? How do we get g of lambda? You see that g of lambda essentially is the negative intercept of the tangent line with the slope lambda. Why would be that? Right? So let us randomly draw a function, a convex function. This is our f of x, right? So according to our definition of the duality, right? So, you know, if I want to get this value at a particular lambda, G of lambda at a particular lambda, say lambda equals to 0.5, right? So according to this definition, right, the right-hand side is some lambda x, like 0.5. I don't know how should I draw. Let me draw it like in this way. Right? This is your lambda x. Okay. So you want to maximize lambda x subtracted by f of x. Okay. In this case, of course, lambda x subtracted by f of x is negative, right? It is equivalent to minimize fx subtracted by lambda x, right? So now, at different x, we have a different gap, right? So let me draw it, right? At different x, I have a different gap, right? If I take x here, I know the difference between f of x and lambda x is this long, right? If I switch to another x, the difference between f of x and lambda x is this long, right? I got numerous choices, right, along this x-axis, right? So now, can you tell me at which particular x this difference is the smallest? How do you prevent? How do you make it perpendicular?
So you're asking about the minimum distance.
Yeah, the minimum distance.
So,
The minimum of f of x minus lambda x, right? The minimum difference between f of x and lambda x, because remember this definition is maximize lambda x minus f of x, right? It is equivalent to finding the minimum between f of x subtracted by lambda x, right? So at which x we can get this minimum? No, not take it dirty. Don't wait. It's not necessary to use that too, right? Just the geometry, right? Global minimum. It's not necessary. It's a what? Oh yeah, I got a point, but let me explain it in a more in a simpler way, right? So basically, I mean, from our intuition, I mean, we can just move this lambda x up, right? And you move until you contact the body of f of x. At that point, the difference should be the minimum, right? So you imagine you move them, right? You move them. Maybe I should draw it. You move them to here, to the right point where you only have one point that overlap with f of x, right? At this position, where at this position, the x star, your lambda x, this line, when we move up, contact with f of x. At this point, the difference between f of x and the lambda x is the minimum, right? If you keep moving, say move here, it will get larger. Right? If you keep moving, right? The difference will be for some places the difference will be will still be larger, but other differences will be negative. So it's not minimum at all. because here we assume f of x is bigger than lambda x. So, so that means we'll move lambda x up to the point, up to a place where that line only overlap with fx at one point. Then that line becomes the tangent line, right? So then the difference becomes the intercept. That's where the gx comes from, a g of lambda comes from. Right? But yeah, you can keep moving, but the problem is that you want to find the distance between f of x and lambda x, which give you the smallest, right?
If we keep moving and then the value becomes small.
No, if you keep moving, they won't change the distance between f of x and the lambda x. That lambda, I mean, this line is not lambda x. It's lambda x plus something, plus some intercept b, right? I just moved that to give you a sense. If you move lambda x, right upward until you just to be a tangent line to fx, then this distance becomes the smallest, right? Because for other places, right, for other different x, this difference, this length will always be bigger than this. Does it make sense? Okay. So by just looking at this difference between these two red curves, right, f of x and lambda x, right, we want to know which distance is the smallest one, right? How can we find that distance? Imagine, right? So you got this vertical line, right? You move from the far left to far right. You know, it is decreasing and then increasing, right? At some point here, you got the smallest one, right? But what's the length of the smallest distance? You want to know that? You just move lambda x up, right, until you become a tangent line of fx. You find that point, right? At this point, this tangent line with slope lambda overlap with f of x. So you know this is the right place where you get the smallest distance, right? Because for any other places, because f is above this function body, right? So you know this guy, this line must be larger than this line, right? Be longer than this one, right? And this line must be longer than this. Why? Because you know, because they are in parallel. So this part, they are the same. They have the same length. So when you move away from x star, no matter it's to left and right, you always have extra length beyond that tangent line, right? So it will be bigger than this particular small piece of segment, right?
Would you mind giving like a concrete example? Say like x transpose x, how would you find the?
I won't have time to give you a concrete example. But when we talk about variational inference, especially local variational inference, I will show you how to use this convex conjugate to find g of lambda. Or in your homework, you can do it by yourself. Then you get to know. Any other question regarding this? lambda is fixed here. Remember, that's where we get this g of lambda. So we want to know at each particular lambda, what's g of lambda. So here we're going to fix lambda. We're going to vary x. We want to know at which particular x this guy is maximum. In other words, at which particular x this distance is smallest.
Each lambda, we're gonna get like a function. So g of lambda is an actual function.
G of lambda is function itself. So it's a mapping, right? For each particular lambda, you have a g of lambda, right? For another different lambda, you have g of lambda. So actually it's a mapping, right? It's a function. Lambda is I mean, if I mean, in general, it's just a real in the real space. So you can imagine lambda here is corresponds to slope, right? Now, if you change to another lambda, right? Say your lambda here, then you have a corresponding lambda transpose x. It's like in this way. You can use the same argument to find that your g of lambda will be moved here. And then at here, you're going to have the difference between the function value. Well, I think it's hard to draw. The distance between the function value and your lambda x is the smallest. Yeah, I intersect twice, but my job, let me, it's a little bit, so this is your log fx, right? So now, remember, I can draw up to lambda, say lambda here, lambda x, this is a lambda, right? So now I want to maximize the difference between lambda x and ffx. Right? So, you just look at this vertical length, right? You want to see which one give you the maximum. This corresponds to different x, right? x1, x2 to x3, right? So lambda x subtracted by f of x is just to connect the y value at these two curves and say what's the difference, right? So now you want to find the maximum value between lambda x and f of x. So how can we do that? You just move lambda x now downward, right? Downward until you find the tangent line, right? You know the difference between your lambda x and your tangent line at this particular tangent point. This length is the largest, right? Because when you move away from this point, right? You from here and from here, your length both decreases. So, and then your g of lambda is just that distance. Because g of lambda is lambda x subtracted by f of x, right? It's just that distance. And, and this distance essentially is the negative intercept of your tangent line. So I know this is a little bit hard to like capture in 5 minutes. I just want to give you an intuition. I speak very slowly about that, but I guarantee that if you spend a half hour after class to look at this, you'll get to know the meaning. But just remember, all this has some geometric interpretations, and have some geometric understanding for this will help you a lot in understanding this. Okay, so I will leave you as an exercise to look at this and try to understand the geometric meaning. And later I will point out the reference to explain this. Okay, talk to you on Thursday.
I'm just trying to figure out like where is alpha to find, if we're supposed to derive.
Oh,
And
sorry.
then
Alpha should be here. It's in front of XX transpose.
Okay, and
Yeah.
then it's the same, like, where's sigma?
What's wrong with that? Why there's sigma? Oh, sigma is alpha here, and alpha should be in front of XX
Okay.
transpose. Yeah.
And then last one, let's see, I got that one. What are we deriving here? Like which partial derivative?
Oh, there must be something wrong with that. Why you see this?
Is
Yeah, it's
mine
the-
different, huh?
It's not. It shouldn't look like that. Right? So give me 1 second.
Yeah, sure.
Let me close the. Let me close the stream first.